Hi, Steve. Can you hear me?
I can, yes. How are you?
Okay, I'm okay. How are you?
I'm okay. No baby yet?
Not yet.
Holding on.
Yeah, like, uh, it's pretty soon. So, they said so originally they said end of October, but then they moved it forward to October 16th.
Right.
But now
And
it's like anytime.
and will this be your first one?
Yes.
All right. Your life's gonna change.
Yeah.
Not see
No
you
more,
again for 5 years or so.
no more Kaggle. I'm just waiting to when he can start coding. So he's like, okay, you're going to run my experiments.
I tried that with my kids, but they weren't interested.
No.
Yeah, like now I'm working from home. I thought I could rope them in to do my work for me, but I would probably have to pay them more than I earn.
Okay. Yeah, they're too smart. Huh? Like,
Yeah, too lazy.
oh man, this competition is like a torture.
Yeah, I know. Yeah,
Oh my God. You, yeah.
it's yeah. I just like spend all my time shuffling brain images about without actually
Yeah. Yeah.
learning anything yet.
Right, right. Yeah, that's the. I see lot of the top competitors have just stopped.
Really?
They're
Yeah.
like, yeah,
Yeah,
they just.
we aren't
Hey,
learning and the models aren't learning. So it's like
yeah,
a
we aren't learning, and the models are not
deep,
learning.
deep non-learning.
Yeah,
Yeah. Although if the top competitors
Okay,
have
we can
stopped,
get going.
that's more chance of us winning.
yeah, that's true. Yeah, a lot of the top competitors they haven't submitted like for 2 weeks, 3 weeks, even a month. Yeah,
All right, maybe they're just waiting to see.
yeah, yeah. Anyway, yeah, we can start. Yeah,
Yeah.
Yeah, so I mean, at least as far as I'm concerned, I keep trying. I wanted to try something, tried a bunch of different submissions uh, with the DenseNet, with weight decay, um, with dropout added, because I thought regularizing would help kind of, the cases where the model isn't learning. And after a few epochs, maybe even somewhere in the range of 2 to 5 epochs, the validation loss begins to increase. So I thought weight decay might help because that's L2 regularization. So I added that, and actually the graphs did get better, but the results didn't. So it's kind of like, okay, the pictures look better, but the again, marginally. I mean, I wouldn't say they got dramatically better, but they improved somewhat. The validation loss, while still spiky, did continue to go down, unlike before where it went up. But
mm.
regardless, the choice of models didn't help. And the other thing I saw was there's a dropout option in the DenseNet configuration. So I added that and increased it to 0.3 even, I think, and that didn't help either. That continued to, and then I said, let me use a ResNet instead of and by the way, I tried slicing, as I mentioned, um, kind of picking some 32 slices, 16 slices, but the thing I quickly realized, because my job started crashing, is if you because in the configuration of the DenseNet we have this thing of I think the input uh, is 16 or 64. I forget now off the top of my head. But more importantly, I think the growth factor is 16, which is one of the parameters of a DenseNet. And um, if your slice in the depth dimension is less than 16, then it kind of I wouldn't completely debug the reasons why, but I think it has to do with how the DenseNet setup is, so it stops working, meaning it kind of ends up with a funny output. It doesn't have sufficient inputs to create the DenseNet properly or something like that to where it doesn't work. So I had to increase the slices to at least a minimum of 32. And once I did that, then the results weren't any better than using all of the 128 voxels. So, and then finally, towards the end, I thought, okay, let me use a ResNet instead of a DenseNet. So there's something called a high ResNet in Monet, and I configured or just tried to build a model with that. And I'm still at a loss as to why, but the 128 voxels option is consistently running out of CUDA memory when I run with that model. So that's at least what I was able to see. So I went back to 64-bit voxels and I just submitted a run. So we have to see whether that has worked and whether it's a problem with the SNet models or what, but something else to keep in mind. And the reason the DenseNet, the thickness being less than is something to keep in mind if after segmentation, Steve, you were to use like a DenseNet model.
Yeah.
Then we need to kind of figure out what would be the appropriate DenseNet model to use there. And the ResNet model, for some reason, I'm unable to, I'll figure it out later today or tomorrow, but that seems to run out of CUDA memory very quickly with 128 voxels. I don't know what the relationship is, or whether it's just Kaggle behaving strangely for me.
Have you got a large batch size on it?
No, I on 128, it used to be with the DenseNets, my batch size of I think 16 used to work fine when I used DenseNet, but it's now running out of memory, and even 8 runs out of memory. So I'm at a loss as to why just changing the model from DenseNet to ResNet should cause the same sized voxels to stop, or the input data is not changed, and it's just the model. Is the model that complicated to where it runs out of CUDA memory between DenseNet and ResNet? I mean, that is interesting.
Which ResNet did you say? ResNet 18 or something bigger?
It's not. It's actually something called a high ResNet, which is available. It's just from what I can tell, it's just a simple ResNet build for 3D models that's available in Monet already. So I just use that. And, because Monet has these choices, right? And there's, of course, a squeeze excitation, but again, in some of those, you need to provide some parameters that I wasn't too lazy to look up. So I said, okay, let me just submit a ResNet and see. And a ResNet, maybe you can try Neol, in which case, at least if it's something funky with my setup, or again, I'm just using the same notebook that's run successfully with DenseNet for multiple 20+ runs, and suddenly it's run out of CUDA memory.
Okay, I see. Yeah, I can try. I haven't tried the ResNet. I'll try it. Yeah.
There's something called high ResNet that you can probably try.
Okay.
I mean, of course, I have in one of my previous notebooks built a ResNet on the fly. Of course, I could also go grab that. I'll try this subsequent trials later today, stop working with this, then I might go back but I can't believe that, just building a ResNet model is causing, but you never know. So.
Yeah, I don't know what the high part is there, like what the high resolution. Like I'm assuming it's high resolution, but I'll check. I'll also try it. And I had little bit of trouble in the past using the ResNet. Like they have a plain vanilla ResNet, and that was not working for me. Like I could get an efficient net to work and the dense net, but not this one. But I can try.
Yeah, that's the thing. I can't figure out why. I might go to using a efficient net and see whether that works. I
Yeah,
can't quite figure out why a ResNet.
yeah.
Is it something with the fact that residual input is directly provided and it's 3D or what? But I can't figure out why it runs out of memory so quickly.
Yeah.
And all your models, are you still all using like 3D models?
Yeah.
Yeah.
All of them are.
And do you think 3D models is the way to go as opposed to just doing 2D models on the slices?
I thought of that.
I mean, I think,
Yeah.
go ahead.
Yeah, I just got. So then, I think I have a very maybe basic question, and that is because how do you when you do the 2D, if you do 2D slices, like uh, we have to classify all of them as class 1, but they might, even though they may not contain the tumor.
Yeah, if you've segmented the model, so
Okay.
you know where the tumor is, and then you just do 2D slices.
Yeah,
I'm not.
that could.
I don't know. Like obviously, I'm not sure.
Yeah.
Is there you might be. I don't know enough about how you identify MGMT. Like it might be that you do need the 3-dimensional sort of space to identify whatever it is that identifies MGMT. But I don't know. Just asking. Do you think 3D is definitely the way to go?
Steve, sorry, when you slice, then how do you intend to deal with this? Let's say, would you use the same number of, if you deal with it as 2D and then slices, are you going to deal with the slices like Mayol was suggesting as LSTM type sequence, or are you just going to use, if you're just using a single slice where it's the largest number of pixels, then it's simply a 2D analysis, right?
Yeah, I'm not sure yet. I'll just share my screen here and show you what I've done so as you can see where I'm up to or whatever, and then perhaps you'll have some ideas about. Yeah, so like this week, I think the segmentation thing is working okay now. So what I did was there's like Brat's 2020 segmentation data, and then there's the task 1 segmentation data from this year. So I took those 2 data sets and I've converted them all in exactly the same way. So like what I do now is, so I took their Nifty files, and by sort of handcrafting them or whatever, I've turned everything into 3-dimensional cubes. They're all 240 cubed. And so like originally, like I was training the segmentation on that and just like using the 2020 task 1 data and the 2021 task 1 data as one big data set, and then splitting that into like a training and validation set. So this is like the weights and biases run on here. So you can see like most of these are from that. So like this is the dice coefficient. So you can see, so like it's up to 1 if you're sort of getting a complete match. So you can see like this is on the training set, like that's all pretty good. On the validation, it was getting like up to close to 0.9, which is pretty good as well. So what I've done now, I changed it over, and now I'm training on the entire thing, the 2020 task 1 and the 2021 task 1, all as the training set. And in this case now, this gray line, that's from it. And like what I'm using for the validation set now is the task 2 data. So basically, like I'm assuming that task 2 data has the same sort of study IDs as task 1 data from this year. So like it does pretty well. And like, yeah, so like it takes a long time to train. This one here is a continuation. I didn't know how to stick it back together again with weights and biases, because like this here's actually epoch 13 or whatever, and that there's about epoch 30 or something like that. Yeah, so like it's pretty good. And then yeah, so like then I was actually came to look at how it had done. So this is like using the segmentation model now it's trained. Yeah, so like this is the task 1 data, and the sort of red area is the prediction, and the gray area is like the ground truth. So this is task 1, and this was like the task 2 competition data. So you can see it's roughly okay, but like then you get ones like this, which weren't that good. So I looked at it a bit closer, and I found that yeah, let me go down here. Yeah, I found, so like this is the task 1 image, and this is the task 2 image. And you can see like here it's like very yellow. And to get this task 2 image, I was using like a bit of code that I'd seen before, which is like this DICOM to array thing, which uses this. Yeah, basically I had like all this LUT turned off and stuff. So it was using like this DICOM pixel array, and then it was doing normalization. So I tried it again, but without that. You can see here, so this is task 1 data, and then this is the matching task 2, and again you can see it's like really yellow compared to it. So I've changed how I produce the task 2 image data now. Basically I just load it and don't do anything else with it, and like once I do that, I get like a sort of nearly absolute match. The two of them are very, very close. Yeah, so somewhere down here. Oh yeah, so here you can see, so like this is task 1 data converted, and this is like now my task 2 data. So you can see the two of them are practically identical. And like that's the old way of doing it. Like anyway, with that I get even better results. So yeah, so like that was the old way of generating it. Like this is the new way. So again, the red bit is the prediction on the segmentation and the ground truth. So you can see like now it seems to have got rid of all of like the little bits and pieces it was putting out. So it's a pretty good thing. Yeah, so going on now. Yeah, so like now I was going to like actually try and use the segmentation. So again here, like these are my predictions. So like each prediction is done, as I say, like it's a 240 cube. So like then I predict on like each slice of the cube in the whatever it is, the axial way. So like here, like this is the image in task 2, and that's the prediction. So you can see the tumors are here, and yeah, like it is doing a pretty good job at finding them. As I say though, like I'm making the assumption that task 2 images are the same as task 1. But here, yeah, like so I ran through to find out which images have the largest difference between task 1 and task 2. And so like this is like them all drawn out. So you can see here, like this one now, this looks to be a completely different image. So this is the task 1 584. This is task 2 584. So you can see that they look completely different. Like this one here has got all the spaces and stuff, and these ones are different. Where the tumor is different in this task 2. But like if you look at this image here, this 584. This one here, task 1's image is missing completely. I'm not sure. I haven't tracked down where that's gone yet. And then this task 1 image here, this looks to be very, if you look at the tumor sort of areas, it's sort of like got a circle and stuff. And like down here, task 1 seems to match with that. So I'm not sure if some task 1 images have been given different IDs than the other thing, but I haven't got to the bottom of investigating that yet. But yeah, so
Steve, just one comment there is, I think if I didn't, I'll post it on Slack. But there's one notebook which did. He didn't do what you have done, which is the image comparison, but he just did, I think, the comparison of IDs and between task 1 and task 2. And he has the list of, I think, task 2 images not present in task 1 or vice versa.
Well, there's actually, there's 8 that are missing. So yeah, like here, so I went through like looking for, so this is the ID from task 2. So like I went through my task 1 images and my task 2. Task 2 has all the images, and task 1, like was missing these 8. So like I've removed these 8, but there may be some images in task 1 that aren't given the same ID as task 2. And like so like that's maybe why like this occurs, where like hopefully it's not something in my conversion, but like everything else like seems to match up, but there do seem to be a few that don't match. But apart from that though, so like again, like I ran the dice score on it, so like with my new converted images, so this is the dice score. So like the dice score for the full data set, so that there's task 1 on the model, which is 0.75. Don't know if you can call that percentage, but it's 0.75 dice. This one was like with my old images. And so like this is the dice score on the new images with the model. But again, like, so like this dice score is comparing task 2 images against the task 1 segmentation mask for the image with that same study ID. So it may not be right, but like as I showed you over here, if you just look at the wherever it was, just look at the so like this here is just all task 2 images. So you can, these are all task 2 flare images. So you can see it does look like it's doing a pretty good job. Just looking yourself, you can see sort of where the tumor is, and it seems to have identified the region. So like I think it's as like good enough to start with or whatever. So like now we should be able to take just like this region, like around about here, and then you should hopefully be able to like tell sort of if a pixel has a tumor in it. And so rather than like working on the whole big massive image, we should now be able to just cut this down. But so this slice that's being shown is the slice that has been identified as the slice with the most tumor pixels on it.
This looks great actually. So Steve, like once you, so now like we could put a 3D bounding box, right, based on the segmentation mask, and maybe I like what you said, like just once we maybe save that as a numpy, even like Srinivas and I could try on the segmented, like on the segmented volumes instead of the full volumes. We could, and we can try both 2D and 3D.
But the thing to keep in mind there, though, Mehul, is the segmented volume. If we just use the segmented output, will not be usable, because the segmented depth. I mean, if we want to patch, and if we have to patch, then the segmented volume should all be of the same size.
I see.
So it can't be that X, Y, and Z is different for each segmented volume. It has to be the same, which means you would then end up selecting either the minimum or the maximum. If it's maximum, then you would be wasting all of the minimum. If minimum, then you'd be throwing away a lot of the pixels of where you have more. You see what I'm saying?
Yeah, so is that when we sort of discussed, yeah, so you could cut it down into cubes. Otherwise, yeah, you could stretch.
Yeah.
But that's where, though, Steve, the simplest thing I was thinking of, given your what you were asking earlier of 2D, the simplest approach could be that you just take as a starting point, you just take for each type, just take the slice that has the maximum number of pixels, in which case you have reduced a 3D problem to a 2D problem. And the 2D is just 240 by 240, but you just use, the slice which has the maximum number of tumor pixels and try just classifying based on 2D with a densenet or a resnet, whatever. You see what I'm saying? That way, then you don't have to worry about. And now, what the segmentation has enabled you to do is, you don't crop away from the 2D the additional memory, the additional brain pixels, but at least it's gotten you the slice that has the maximum number of tumor pixels for every image.
Yeah, but you're not throwing away like a lot of stuff then. So you could, can you see like this picture here? So like it's pretty, this here is actually not with segmentation on, but like the segmentation would show you which of these slices here had the tumor. So you can see that, yeah, like there's maybe, I don't know, there's 16 per line. So there's maybe like 48 slices here, which have a good example of the tumor. And then, yeah, like that's out of 240. So there's 200 slices or whatever don't have that much tumor. So yeah, you can like instantly sort of drop sort of maybe 200 slices and cut it down to 40. And yeah, like then use all of these slices here, they're in the middle.
Yeah, but that number is going to vary for each.
Yeah, but does that matter? So like, yeah, so say that this is a slice that has MGMT. So here you can give it like 40 examples and say, yeah, like here's 40 examples with MGMT equals 1.
If you handle it as 3D, then yes, because every cube passed to a 3D, just like every slice passed to a 2D, has to be of the same dimension.
Yeah, but every one of these slices is the same dimensions, isn't it? If you're not
yes, but that's why I said that but for a 3D, for a 3D, as analyzed as a 3D, then the depth also has to be fixed. It can't vary from, if you're batching it, if you have 8 images in a batch, every 3D image within that batch has to have all 3 dimensions identical.
Yeah, but sorry, I thought you were saying if you did it as 2D, you would just take the slice, take a single slice and take the single slice that had the maximum number of tumor pixels.
Yeah, that's the simplest. If you did it as 2D, I was just saying that's a simplest starting point, but you can always do it as 2D and then unroll, like using an LSTM or something that Mehul was talking about, and a couple of people have done that. Then you can have the slices as, each slice is like a time sequence thing, right?
Yeah, sure. But I was suggesting
Meaning,
for the 2D model, you don't need to just take a single slice that has the maximum number of tumor pixels. You can take all of the slices that have tumors identified on them. So like from this single DICOM image, you can take what 50 slices here. Like all of these middle ones have tumor. So like all of these, you could take all of these and put them into a 2D model. And like each one of them would have the same MGMT value. And you know there's a tumor on it. And then like similarly for if this one on the left-hand side was MGMT equals 0, again, you can take all the ones with tumor and put them in. You don't need to take one single slice, because if you take one single slice, you're like throwing away stacks and stacks of data.
right, in which case you would do it as you're saying, what would your network structure be, or
Yeah,
you would provide?
Yeah, it would just be a 2D CNN that each one of these images here is 240 by 240. Each 2D slice is 240 by 240. So yeah, like here you would just have whatever that is, 40 different 40 different images as input.
Yeah.
Okay, so you would just increase, like basically duplicate the NGMT values and just provide a lot many more of the same type, but saying they all have the same study ID, but NGMT value the same, and then just increase the number of images input as 2D.
Exactly, yeah.
Okay.
Yeah, and it's quite nice. So then, I guess when you were just talking, one way of thinking is then we classify each slice as MGMT positive or negative, right? 1 or 0, and then on the test set, say you have 100 slices, and let's say we just do the majority, right? Like say 45 were classified as non-MGMT, and what? Oh no, you're going to segment. Yeah, you have the segmentation on the test also. So let's say after segmenting, you get 50, and 30 are 1, and 20 are 0. We can do majority class, or I mean, there's so many ways to combine.
And that leads to this question, right? How would you then handle it on not the validation, which I assume was what Mehul was referring to, but on the test side of things?
Steve, we would run the segmentation on the test.
Yeah.
Right, and then pick the slices which have lesions.
Yes.
Yeah, and then pass them through those 2D CNN.
Yeah, and like there again, so like at inference time, if this was the test image, so you would identify using the segmentation model which ones of the slices had the tumor, and then you would put all, say, 40 of these through the test thing, and like then I don't know, take majority voting or whatever to see what its prediction is onto the MGMT.
Yeah, I think this is great. Yeah, there's so much to try with this segmentation. It's like nice. I think so when we do individual slices, we lose the 3D effect, right? The 3D, like the spatial position. So another, like I think you guys already mentioned, is pass them through. Can we pass these slices through an LSTM? So the one approach I saw, the one notebook I ran, was they pass it through a CNN first. No training in the CNN. It's just a pre-trained ResNet. So for each, basically you get a feature output, right, at the end of the CNN, and then it's so for each slice you have a feature output, and you can consider them as vectors, and you pass that through an LSTM. But how would you? But yeah, I think the sequence modeling will be critical to like get that 3D So like the 3D positioning stuff. And I actually read like the winning entry in the CT classification was basically with uh, running a 2D CNN and then sequence models. Um, but I'll share that. Yeah. But yeah, Steve, yeah, that looks great. The segmentation. Yeah, because I don't know, with the 3D models, I'm just like losing hope.
Yeah, well, obviously you can still try the 3D models on it, and yeah, like as we've said, um,
Yeah.
the paper I saw that said that it had done well at MGMT identification. It was using a 3D model, and it used the segmentation, and then it used the 3D model, and it said it used, once it had like identified sort of roughly where the tumors were with the segmentation, it did 32 by 32 by 32 cubes going into its 3D bit. So yeah, we could try that and see.
Okay.
So
Mm-hmm.
yeah, so like now the segmentation thing, I think it's okay. So yeah, like I'll share it with you guys like tomorrow or Monday or whatever. Obviously it means you would have to use my input data as well. So hopefully it's okay.
Yeah, that should
Yeah,
be
I
fine.
mean, obviously we'll need to switch to the data that you're using in order for it to be consistent. But I mean, it is what it is, right? I mean, that's a foundational aspect of the problem, which is why I said getting the segmentation working is kind of paramount to everything you can do downstream, because um, that's foundational, meaning we must, or we have to use the data you're using for it segmentation to work, which means that's the bigger problem to get right anyway, as I was saying. I mean, the classification and other thing is by comparison a trivial thing, although that might also require a lot of trial and error, but it's more trial and error than in your case, I think you had to do a lot of engineering work to figure out what worked, what didn't. I mean, this is more trial and error.
Yep.
And
I
2D
put a
models,
Kaggle
the
discussion
other good
about like
thing.
some. Sorry. Sorry.
Sorry, go ahead, Mehul.
No, you first, then I'll just.
The 2D model thing, the other thing I like is so from the segmentation, what I was about to say was the 2D models should help with the speed aspect too, because now we are just using 2D models, which are a lot simpler computation wise than having to do it in 3 dimensions, because it's like an entire dimension of multiplications, matrix multiplication that you don't have to do, which is tremendously useful, even if you increase the stack of 2D multiplies you do, but that they're not comparable. I think the 3D is much more complicated, so it ought to run that much faster. But the question that I was going to ask Steve was, so how is your segmentation identifying, or would we does it spit out when the tumor is 0, or does it spit out like the starting frame or slice where tumor pixels first appear to where tumor pixels disappear, to use the number to kind of identify the slices we should use in the
yeah, like at the minute I've got to take like one study and then loop through the 240 slices in that study, doing the segmentation, and then asking, then I sort of like count the number of pixels in the return mask. So at the minute it's giving me a mask back, which is like a binary mask with set to 1 if it identifies a tumor and 0 otherwise. yeah, so I was just working now to, like create like the NumPy arrays that sort of match with that for the training set. The other thing is sometimes on like an individual slice, you might actually get like sort of two tumor regions. That seems to be just like if you've got like a large tumor or whatever, and if it's like a lower down slice in your brain or whatever, where you've got the brain stem, it sort of can be either side of that. So in some ways, like that makes it hard to draw. It'll like identify there's tumor on that slice, but if you wanted to sort of identify the bounding area of the tumor, it's slightly more complicated if there's two separate areas. So yes, so as I say, like at the minute, if you want to identify the tumor, the slice that has the maximum tumor on it, you just have to put it in a loop to like get the segmentation mask for each slice, and then count the number of pixels until you find the one that has the maximum. Yeah, so
Right.
I'm
No,
just
but I was
doing this
saying
now.
if we use then, yeah, that's more complicated than based on what you're saying. Then the easier approach would be what you originally suggested, which is just pick all the slices where tumor exists, in which case the thing that would be great is if the segmentation eventually spit out a start slice and an end slice for every study, that in your 240 by 240 by 240, which then is the set of slices, because over those slices, you'll need to duplicate the MGMT value.
Yeah. The only
that
thing I
that
found
study
is
has.
though, sometimes it's not as easy as having a start slice and an end slice. Sometimes there may be multiple tumors in the brain, and so you may get multiple start and end bits. So if you're going from the top to the
Oh,
bottom, you might find like some slices have it, like say like 10 in a row, and then there's a gap with none, and then another 10 that do have it.
But that shouldn't be a problem if we are just stacking the slices to 2D, right? Because it just increases the number of slices which have tumor for the same study. It doesn't really matter whether they are contiguous or whether they are not.
Yeah, but in terms of like sort of training your model or whatever, you want to just find the slices with the tumor, and you don't want to run the segmentation every time. You want to run that up front to speed things up.
Right. But what I'm saying is, once you run it, and even if your segmentation output is giving you is identifying multiple start stops, right?
Yep.
That should be okay, right? Because it just means, because eventually if what we are doing is just feeding for a single type, for a single study, right? If you have, let's say, 20 slices in the beginning and 20 slices at the end, which both have tumors, for example, then if the segmentation says start stop is at 2040 and then again at 8000, all we are doing is combining those, and for the same type, say a flare, for the same study, and feeding it to the 2D classifier, but instead of feeding 20 slices, we'll be feeding it 40 slices. But who cares if they are contiguous or not contiguous?
Yeah, not exactly. Yeah, but yeah, so like that's just the work I was doing at the minute. Was like now I've got the thing. Yeah, I was just running through, sort of seeing what was given me. So I was going to produce like like a CSV file or whatever that has the list of all of the task 2 images, and like which slices have which indexes have tumors on them. Yeah, so we can do
Right,
that.
because
We can
all
do
this,
that up front for training. Yeah.
yeah, eventually what we need out of the whole segmentation pipeline is a maybe even disparate, but by disparate I mean non-contiguous sets of slice indices that have the tumor, and we can just, and then we'll need to duplicate MGMT for a study over all the slices that we pick to have the same value. And all those slices which have the tumor should then, for that study, be combined into, the set of images that we end up using.
Yep.
For that study, and then feed all of the sets for a particular type into a same classification pipeline, and then ensemble like the current pipeline does. So it's matter of, so all the segmentation I'm just thinking through is generating a set of 2D images that for any particular type that then get fed into the 2D classifier.
Yep. Yeah. So yeah, like all of that's pretty much working already. So I'll just tidy up the notebook and I'll release it to you guys tomorrow or the next day. And yeah, all of the data for it. So like all of the 2020 and 21 task 1 data, it's all public already. And yeah, my converted task 2 data, I've only converted Flare and T1W at the minute. But yeah, like it's public as well. So you should be able to get all of that. And then you should be able to just run the segmentation
I had
thing
a
yourself.
question, by the way. Yeah, I had a question when that was on the back of my mind when you, which was prompted by what you just said of you just converted Flare and T1W. So let me state what I think I understand and then see whether you guys have any comments. So the reason to use all 4 types is primarily because we don't know which of the types in the test set would end up giving us necessarily better results, right? Because otherwise I was thinking there's no reason why if we consistently train and find that 2 of the 4 types are better, that we must use all 4, other than the fact that we don't know whether the same 2 types will give us better results when used on the test data. Am I right in that, or is it more complicated than that?
I think Hill would have to answer this one, but yeah, like that's the sort of idea I was going with, that we didn't need all 4. And the only reason I didn't convert all 4 was because of the fact that Kaggle data sets were complaining because it was getting too big. So I only converted the ones that, yeah, Flare because of the fact that it looked as if the tumors were easily to identify, and T1W because it looked to be sort of one of the common ones. But yeah, I would just need to create like another data set for the other 2 if we need them, but I don't know if we do.
Yeah. So like, like I was telling last time, the T1 contrast is the one where the contrast goes in the tumor, right? But yeah, not sure. So I started a Kaggle discussion thread with like some of the papers I found, just to see if and so it's like three it's the papers which do MGMT, and there were 3 papers which did it. And one surprising thing, so T2 and Flare are very similar, except that the water is suppressed on the Flare. So in the middle of the brain there is water, right? So that appears bright on the T2 and black on the Flare. Flare stands for fluid inversion, blah blah blah. Some repair, I forgot, but it's basically, so it highlights. Flare is supposed to highlight the tumor but suppress the other water, right? So the interesting thing from the papers is 2 of them reported they got the best results with the T2 weighted, and I was surprised because I didn't expect that. And it was 2 different groups at 2 different times. One was from 2016, and I think another one is from 2018. I'll share the thread. And then someone else reported in the comments that they are also seeing better results with T2 weighted. But yeah, that is, of course, a lot of it is random. But yeah, we can, yeah, we can, yeah, we don't know what will happen on the test set. So maybe do all, like, if we have time and space and memory, we can do all 4. But maybe we can start with
that is the main reason to do all 4. Am I right, or is there anything more complicated than that?
I mean, from biology, like it's the T1 contrast agent is the only one where the contrast region goes into the tumor, right? So I don't know if that helps us in any way. Like maybe, like, I mean, so I'll give you an example. Maybe the MGMT 1 tumor is more porous than the MGMT 0 tumor, but I don't know. That if that was the
Okay, so
case,
biology is another reason besides the
mhm,
fact that we don't know which, if
yeah,
there is change between the training set showing better results, predictability from one particular type versus the type, because of the underlying biology, the type that indicates NDMT is different in the test set. So it all leads eventually either through biology or because of
yeah,
the nature of the images, because of either biology or because of the physical aspects of the images, the type of images could be different. Because what I was, and the reason I wanted to discuss this was, what I was wondering is, if in the training we consistently find that one or the other um, type yields better result, then why are we, why do we feel compelled, or what do we lose if we just use that? And I guess these two are the reasons mainly to not stick. And as you said, I mean, and by the way, the other thing to complete the thought is the paper that Steve posted and referred to, that one uses, as he mentioned also earlier today as well, that uses all four types, and gets, what blew me away was they seem to get better prediction with this radiogenomic thing than from biopsy, because the biopsy has to still process through chemical reactions, right? I mean, just because you get a piece of tissue out, that doesn't inherently tell you whether there is MGMT in it or not. So you need to do some other chemical gobbledygook that guys and gals do to figure out MGMT 0 or 1. And that has some confidence level too, right? Because they can't be 100% certain. I mean, it's a chemical process that you're subjecting the tissue to. So
uh,
with all that said, what
I
blew
think
me
it's
away about the,
sorry,
go ahead.
sorry. This I don't know if it's a chemical process or it's the DNA. So it might be more. There might be more confidence. Like, you can look at the, like, DNA. DNA is like those sequence nucleotides, like A, G, C, T.
Yeah,
Right. Like
right, right. No,
there might be more certainty in the MGMT, but I'm not sure exactly.
no, but what I'm saying is the paper, at least that Steve referred to, said that this methodology gave them, and obviously this is a non-invasive thing, right? I mean, you just go under the CT scan, MRI scan thing and get 4 images taken, blah, blah, blah. But this, according to that paper, this method gave them better confidence, into a better predictive ability than by taking out the tissue and doing it,
I see. Okay.
which I thought was really impressive, because basically it says the non-invasive method is giving you as good as or better than after drilling a hole in your skull and taking the tissue out.
Yeah. Yeah. Yeah.
I mean, that's a big deal, right? Because I
Yeah.
mean,
No.
for
No, yeah. This is.
patient, I mean,
Yeah.
right? So I was, but they then the reason, but back to why this is interesting is all because of they used all four types. So that's the takeaway. I mean, they didn't rely on one or two.
Yeah, so like I've used the flare for doing the segmentation and it seems pretty good for that, but it may be that one of the other MRI types is better for actually identifying sort of MGMT presence. Like I haven't seen that much about it, about how it can tell, but I saw like a little bit that said it was like down to sort of looking at the structure of the tumor is how they think it tells. So yeah, like it may be that one of the other MRI types has more sort of clarity about the structure, as opposed to the flare type, which just like seems to light up the tumor and maybe loses the structure of it. So I've converted the T1W images over, but I'll do the other two as well. Now I know what I'm doing. Like if I make the data sets public, then I can like upload them okay.
Okay.
Sorry, Mehul, were you saying something?
Me about something. I'll be right back. Yeah, I think the structure thing is very interesting because the T1 has the most detail. The T1 is like the pixel resolution is in XY is like 0.5, 0.5. But even if you changed it's still okay because I think it's better than the others. But we can go back to I think Srinivas's original notebook with the analysis and look at the pixel sizes. But yeah, I'll be right back in 2 minutes. I just need to do one small thing and I'll be right back.
Okay. Yeah. So like as I said, I've used, it was like sort of common code that was on there, like the thing about identifying, was it sagittal or axial or whatever, and like then spinning the tumors and like doing the thing about putting them into like left and right and front and back order and stuff. So I've applied that to everything, and like it's done, like just using sort of like NumPy manipulation, because I tried using Mehul's notebook using the sort of the official Bratz manipulation, but it was like far too slow. So all plus as well, like some of the scans are different resolutions to others, whereas like I've standardized everything on these 240 cubic things. So I don't know, like, will that have any sort of impact because of the fact that I have sort of stretched or shrunk the images, but now they all are sort of the same and like all the same size.
But what?
Yeah, like for all of the scans, it means that the segmentation matches up exactly to each one of them. So you don't have to go and like look for the segmentation on each of the different types. It should be all in exactly the same position, hopefully.
Yeah, the what I was going to say was the data that Mehul and I are using is also being done. Similar things done. I don't know exactly same, but similar things, right? Because when we use the 64 voxel or 128 voxel, it's done the same thing. It's stretched or pushed or basically gotten everything into a 64 cube voxel. So you've just done it to 240. But I'm kind of surprised that he did it for 256 too. So there is the 256. The thing that makes this really hard is and which is part of the reason Mel was saying that it's so frustrating, is one is getting the segmentation part, which is, as I keep saying, the hard part which you got working. But the other frustrating part is when we do 3D, and which is why I think the 2D approach might be a heck of a lot better, then we run into memory issues when we are handling 3D voxels. As soon as we handle 3D voxels of any shape greater than 64, then we run into even for 64, the batch sizes have to be reduced, and not terribly. Thankfully, there it seems to work for 32, but again, as soon as you use ResNet, I don't know whether it works. I don't know what the interaction is between, the type of network and the 3D models, but that's the other advantage of what you are suggesting of a 2D approach after you have segmented it, because I am assuming that the number of slices you throw at a 2D shouldn't make a whole lot of difference, because that's not what is, that doesn't have any impact on the memory storage because it's all transient anyway. So you can throw tons and tons of slices at the problem, but as long as they are 2D, I'm hoping that we don't run into this CUDA out of memory because we're no longer using 3D.
Yeah, and the other advantage is if we go to like 2D, then you can use like the whatever it is, Monet. They've got like the pre-trained 2D ones, don't they? Where they don't have pre-trained 3D.
Yes, I believe so, right? Because I think they have a 2D trained models. Yeah. So if that is a pre-trained model, we could use that pre-trained model. That's an excellent point too.
Yeah. One other thing, I've lost it now. I can't find it, but oh, yeah. In the discussions, I saw that somebody posted up it was like a list of previous competitions in Kaggle to like do segmentation of brains. But part of it was like saying about one, and it had, like I think it had the 4 different MRI types again, like whatever. But it was also saying about there was one where it thought that you could, it had information about which of these had MGMT and which didn't have MGMT. Because like obviously if we could find other data sets that identified MGMT, it would be good. I'll have to like look for it again, because yeah, like it seems obviously we're sort of pretty limited in what we have at the minute.
Yeah, let me look.
So you're saying
for additional data.
Yeah, it was like somebody was like saying, and like it said it had 4 different types of stuff, and it said whatever it's called, glioma or something. It said, and it said, oh yeah, you can like use these as positive for MGMT, but I wasn't sure if you could or not. I'll have to find the discussion again. I can't find it at the minute, but.
Yeah, so Mehul, what Steve and I were discussing when you stepped away was, I think the Monet guys have a pre-trained 2D model. Is that correct? Is that what you remember too?
Pre-trained for what?
For pre-trained for brains?
Brains, yeah.
No, they don't, I think. The Tencent guys have some.
So I thought the Monet guys were. Remember we said, oh, we can't use it, but because it's pre-trained, but it is pre-trained, but pre-trained on. Anyway, I'll also check it out. But I thought it was on the 2D. Yeah. It was pre-trained, but it was pre-trained on 2D. That's the reason we couldn't use it on 3D because the dimensions was 2.
Yeah, right. I remember seeing, it was pre-trained, but I didn't know if it's pre-trained on just ImageNet or like actual medical images. But I'll check that. And you're right. It is pre-trained, but I just need to check if it's ImageNet or real MRIs. The one other thing, so this problem has been around for a while. So I think the earliest paper I saw was 2012. Okay, so there's even some, so the non-deep learning approach, right? So now you have the segmentation. So what they're doing is they just find a lot of features around the tumor and inside the tumor. So features like some make sense, right? Like volume and some mean intensity or skewness of the intensities. Maybe the change in the variation in the intensities tell you something, and they also but they also do like texture. They're looking like some features to measure texture. So one of the so basically the idea is completely non-deep learning, right? You do segmentation with deep learning, then extract features with image processing, and there's already a Python library for that, PyRadiomics. I'll share it. They just, it's just features, but they always come up with fancy words. They call it radiomics. So I'm like, okay, just say whatever. And then it's just XGBoost. And then you can do feature importance, blah, 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 all that stuff. Yeah. But then, you could even input those.
You could at that. Sorry, go ahead.
You could even input those features into a full, into a dense neural network. Yeah.
I was thinking you could just combine the features, concatenate them with the output of what your conventional, neural network gives you, and spit them out through a couple of linear layers, right?
Yes, that'll be fine. Yeah.
I mean, you just take the features and take the output of what your convolutional neural net you chop off the head, whatever your CNN network, because we are now using a conventional CNN 2D, take that. Basically, it's extracting a bunch of features from the images too, concatenate that feature with the other feature extractor output, and then pass it through a couple of linear layers, and out pops the result.
Yeah, I think that makes sense. Yeah, they can do. I saw one paper like the previous competition also doing some concatenation exactly the same way. Like take the CNN out. They did like a CNN output, LSTM output, and like the feature and some other like DICOM features. Like they were putting in slice thickness as a feature, for example. But, okay, yeah, that's it. Steve is highlighting that part about the glioma. Yeah.
Yeah, so this is the thing I'd found. Yes, like this guy here is just like listing other data sets related to brain thing. But it was this bit here. So he said like there was like this competition in the past, and yeah, like it was like classifying 4 different types of brain tumor. But he said like you can change 2 of it. So in their competition, they have ones tumors which are non-tumors and ones which are glioma tumors. And he was like, here you can change 2 of them. He says to make it glioma tumor with MGMT and glioma tumor without. I don't know if you can do that or not, but like if you can do that, then we could take this data set. If these ones here are MGMT, we could take it and add it in as well. But I don't know if you can do that. Or I don't know why he, because I went to this competition here, whatever it was. Yeah, so it doesn't mention anything about MGMT, but I obviously don't know enough about brains or whatever to know if a non-tumor glioma is the same as not MGMT or whatever. But
can you share this link? I'll check and just
yeah, so I'll share that. Yeah, so it's in the chat now. So. Yeah, like as I've said before, that paper that I'd shared that did well in the MGMT thing, it was mentioning some MGMT data set, but I haven't had a chance to go and look to see is it publicly available.
Okay.
So in the networks that you've actually trained, do they look as if they learn on the training set? Does the loss actually reduce on the training set?
Yeah, on the
Yep. In all cases.
Yeah. Yep.
In all instances, all types, the training set loss goes down significantly.
Right.
And consistently.
Yeah, I've been trying. Yeah, I think same as and same for I tried some 2D model with LSTM. Same thing. The training looks great, but and then the submit. I had a question. Like so, I for the random submission, right? When you run simulations, like you get a like you can see that the mean 50th percentile is 0.5, and then but this other guy he extended my analysis and he said it's because we are making 20 submissions, 50 submissions. So I don't know if you had a chance to look at that notebook because I'm trying to figure out what score is like not random.
Yeah.
Because I saw one of the notebooks even says they went from 0.54 to 0.71, which is pretty high, from which I thought they went from to 0.71 with just changing the random seeds. So that is like that makes me very depressed. I really thought like a winning score in this competition would be 0.85. But like, somewhere 0.8, 0.85. But if 0.71 is random,
no, but I don't know about this competition, but if you read Steve's paper, their results are in the 0.9 domain. I thought definitely more than 0.8, high 0.8 or 0.9, which means that somebody out there with some data set has achieved 0.9 results on exactly this problem.
Yep.
Now, it may be that we don't have the right data, we don't have the right set of inputs, right test set. And this is a question that I've been struggling with. I kind of, again, would like to hear both of your thoughts is, how do you tease out what you are saying, which is, oh, the model doesn't learn or hasn't learned well enough, and separate that from our test set is so small that it introduces randomness in how good your results are. Those are two separate problems, but the output we get, or at least what we are staring at, I have not been able to tease out how to separately, how to kind of say this part of the swing in the result is because of, the test set being small, and therefore some level of randomness you're going to get no matter what, versus, oh, a model isn't learning well enough and is not generalizing well enough. Do you follow my question?
Yeah, but I'm not sure what you can do about it. Yeah, like that's why I was like sort of saying if we can maybe find some more MGMT data from elsewhere, and so we can increase the size of our test set. And like, yeah, the public leaderboard, it's like hard to go off their scores, isn't it? Because it's such a small test set. Whereas if we could find extra data ourselves, then we would just have to go with our own sort of validation.
Increase the confidence in our validation set.
Yep.
Yeah, I think that would be a good way to then separate out, at least minimize the problem of a small test set. Of course, we still need to ensure that our model is learning well. Let me, for example, since you asked Steve, let me share maybe one of the, if you guys can see it. Let me maybe share this notebook. Can you folks see my screen?
Yep.
Yes.
So here I was trying, weight decay on this 128 voxel thingy. So you can see actually, the thing I was surprised was, look at, this is my training and this is my validation, but you can see how bouncy they are. But part of the result was I had used a very high weight decay of 0.01, I think, for this one, if I'm not mistaken.
Yeah, so like there, do you think that's actually learning at all? Like the training loss isn't really decreasing?
Yeah, see, this one looks bad, right? Now, on the other hand, the without weight decay ones. Let me show you that, because that is actually which kind of was then weight decay. Okay, it just happened to give the best score, but doesn't really mean much because the next identical run with a different seat varied by 0.05. The reason I said what I said in response to what you asked, Steve, was that.
All right, yeah. Nice. Although still a very high loss, isn't it? But
yeah, I mean, but it goes from 0.69 to about that. And you can see at least it's consistently going, I mean, barring this spikiness, but you can then see about here, the validation loss takes off. Takes off meaning, it goes, but if you average, it's about here.
yeah.
So it's increasing past this point, right? And then you can see how the EUC is. I mean, it kind of gets to this point and then it goes around there. So in fact, that's when I switched. Originally, I used to use the highest AUC, but then I switched to using the loss. Because that says if I'm using the loss, then I'm using the value of the model corresponding to the lowest validation loss, which is about that point, which in a sense is about the average of the EUCs. So I expect that to generalize better than just picking maybe the model at this point or at that point, which would be my choice if it were based on the EUC score of validation. And you can see the nature of the curves is pretty similar for the different types. You see that one? But here again, you see for some types, even the training loss doesn't, from 0.7, it's just gone to 0.68.
Yeah.
And then in this case, it drops. It's about maybe the lowest is here, but it's about low here. And then again, it begins to rise. So the model overfits very easily. And it varies from type to type. That's why I was asking the earlier question of, now here you see, again, it's not a very dramatic drop, but from 0.70 to, I don't know, 6.5-ish, something. Whereas, you see the validation thing, it's like out there and then boom, it just takes off. Even from here, after about a couple of epochs. That's why I'm skeptical that these things are learning much, or the variation is so high, as Mehul and I have been saying. That's why, and again, same thing here, it goes from about 0.71 to about 0.67, but then you see about here, validation loss is lowest after that. And, it's actually not reduced much. It's from 0.69, I don't know, maybe to point, but very little.
Yeah.
And in fact, you can see that to a certain extent from this printout gives you a lot of information because it's episode 5 and right where the loss is minimum and the AUC, the corresponding AUC is this. And you can see episode 7 only in CE, which is this contrast enhanced stuff that Mehul talks about, that it goes to to episode 15 before the loss is minimal. But the EUC in these two is consistently across all the runs is lower than for flare and T2W. I've consistently seen flare AUCs and T2WE seems to be the best. The numbers vary. I think the best one I got was like 640 or something, and here also something in the 0.6 range. But to your point, Steve, you can see the loss is 0.68, 0.69, 0.69, 0.689.
Yep.
So doesn't seem like much learning going on, which is part of the problem that our values are all over the map. I wouldn't say zero, but I don't know how much. Just kind of what Mehul you was saying, right? Like, okay, so what's the, another way of seeing whether it's learning anything is, is it better than chance? And that's kind of what you were trying to, I think, determine by that chance question. Oops, Mehul dropped off.
How's it going?
Yeah. Okay. So I think, yeah, if you can post the link, I'll play around with the classification models and see whether, but I think that's another reason why your 2D based approach might be a heck of a lot better. And we can figure out whether that's learning as well.
Yep. Yeah, so I'll try and get that like shared with the two of you tomorrow or whatever. Hopefully if we start using that. Yeah, I'd wanted to ask Mehul a question about, he put in the sort of the sample submissions where he put in all zeros and all ones and all 0.5s. Yeah, like I thought the results he got out of that were what you'd expect, but I was just surprised about the one. He put one in which was, I think it was all zeros apart from the very first study, which he put like in as one. You'd have thought that if that was working right, that it should have been like a slight variation, either higher or lower than 0.5, because I know that people have been in like leaderboard probing, and like that's what they've been doing. They set everything to zero apart from like one entry, like they do like sort of one hot encoding, and so they can work out is it MGMT or not. Whereas Mehul said that he just got 0.5 back, where I don't think he should have done. I thought he should have got like 0.51 or 0.49. So I was very surprised at that because it doesn't seem to make sense.
Yeah, otherwise, how would they figure out by probing is your question.
Yeah,
right?
exactly. Yeah. So I'm not sure. Was there something wrong with his submissions? But I haven't had a chance to look closer at it. I might try it myself and see what happens.
Yeah, I haven't tried that.
Yep.
That'd be interesting as to how they. But like you say, you would have to probe the leaderboard, and if you dial it up or down, the only way you would know whether you are in the right direction is if your score changes in the right direction. Right? Meaning like better than 0.5 is you're guessing it right, and below 0.5 is if you're guessing it wrong.
Exactly. Yeah, and yeah, like I'd seen like a lot of discussion about it, and people putting notebooks up, which is what they did. So that's how they were doing it. So I'll try it myself and see what happens. Okay, I'll head on here. So yeah, I'll post up my notebooks and like all of the data sets. Yep. And
great. Thanks a lot.
Speak to you next week. Okay. See you later.
See ya.